All right, welcome data detectives. Today, we're on a case. We've been handed a set of numbers, but there's something more going on here, a hidden pattern. Our mission? To crack the code, and we're going to do it together. So take a look at this. At first glance, it just looks like a random jumble of points, right? But here's the thing, they're not random at all. They're telling a secret story. And that's really the big question we're asking today. When things don't move in a straight line, how in the world do you figure out the pattern? You see, when that trail of clues starts to curve and dip, a simple straight line just isn't going to cut it. To uncover what's really going on, we have to pull out a special tool from our detective kit. And here it is, our first big clue. The secret isn't always in the numbers themselves. Nope, it's in the change between the numbers. The real story, you see, is written in those gaps, those little jumps from one point to the next. Okay, so to analyze those gaps, we're going to use this really cool technique called the method of differences. Think of this as the #1 tool in our detective kit. It's specifically designed to expose the true identity of a hidden pattern. And the best part? It's a pretty straightforward 3-step process. First, and this is super important, we gotta make sure our X values are all equally spaced out. That's a must. Then we find the first differences. That's just the change in our Y values. And finally, we dig one level deeper to find the second differences, which is the change in those first changes. It's this systematic approach that's gonna crack the case for us. All right, enough talk. Let's put this tool to the test, shall we? Here's our first case file. We're gonna apply the method of differences step by step and see what we can dig up. Okay, here's the data. So first things first, let's check step 1. Are the X values equally spaced? Let's see, we've got 0, 2, 4, 6, 8. Yep, they're all jumping up by 2 each time. Perfect, we've got the green light to keep going. Time for step 2, the first differences. We're just looking at the change between each Y value. So from 12 down to 10, that's -2. From 10 down to 9, -1. From 9 to, well, 9, that's 0 change. And from 9 up to 10, that's +1. So our first set of clues are -2, -1, 0, and 1. They're all different, right? So we know this isn't a straight line. Time to dig deeper. Okay, on to the final step. Step 3, the second differences. We do the exact same thing, but this time on our first differences. So what's the jump from -2 to -1? That's +1. And from -1 to 0? Also +1, and wait for it, from 0 to 1, you guessed it, +1. Look at that, it's the same number every single time. We found our constant. And this is it. This is the moment we've been waiting for. This constant, non-zero number. It's the smoking gun. It's the key piece of evidence that cracks the whole case wide open. The real pattern wasn't on the surface. We're even one layer down. It was hidden 2 layers deep. And that leads us to the final verdict. Whenever you see a constant non-zero second difference, that is the unmistakable signature of a quadratic function. We've got it. We've identified the pattern. That consistent value proves the relationship here is quadratic. Case closed. So, now that we know what a quadratic pattern looks like, let's sharpen our skills by trying to spot an imposter. We're going to look at a new case file, a set of data that might look like it has a pattern, but doesn't quite fit the quadratic profile. Okay, here's our new data. First check, are the X values equally spaced? Yep, so we can proceed. Let's run the numbers. First differences are 1, then 2, then 4, then 8. Definitely not constant. So we go to the second differences, and we get 1, then 2, then 4. Still not constant. The pattern totally breaks down here. The evidence is crystal clear. The second differences aren't constant, which means this pattern is absolutely not quadratic. It's an imposter. Now, it's probably something else, maybe exponential, but hey, that's a case for another day. What's cool is that this shows our method is just as good at ruling things out as it is at confirming them. So, okay, we've learned how to spot a quadratic pattern, but you might be wondering, so what? Why does this matter? Well, let's zoom out for a second and look at the big picture, because this detective work is the first step to something much bigger. You know how you only need 2 points to define a straight line? Well, it's kind of the same idea here. You only need 3 points, as long as they're not in a straight line, to define the one and only curve of a specific parabola. So identifying the type of pattern is the crucial first step before you can actually build the function that describes it. And that, my friends, is what we call a quadratic model. It's when we take real-world data, I'm talking about the path of a basketball shot, or maybe even a company's profit over a few months. And we find the quadratic function that fits it. All that detective work we just did, that's what lets us build these incredibly powerful models. Now, the next step in a full-blown investigation is using a tool called quadratic regression. You'd usually do this with a calculator or computer. And what it does is it takes the points that we've confirmed are quadratic, and it actually spits out the exact equation for that curve. And that's the real magic, because it turns our data from just being about the past into a model that can actually help predict the future. So we've just added a brand new tool to your data detective kit. Now you can look at a set of numbers and see something more, right? You can spot the signature of a hidden story. So the real question is, now that you know how to look for it, what hidden stories are you going to find in the data all around you?